Para 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 pa pa para 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 pa pa para pa pa pa. Share like this really quick project I put together earlier today. So like I've made the case before that a lot of modern day machine learning work is really has turned into DevOps, as in there's no real consensus around which algorithms, which loss function, which way to pre-process your data is best. So a lot of it comes down to like, can you try them all out quickly and get results back quickly? And so really like at least I mean obviously this does not encompass all of machine learning statistical work, like this is a small subset of it, but it's one that I think is becoming increasingly important. And so I wrote down like some scripts that I think make it a lot easier, where you can like essentially feed in like a bunch of arguments to try, schedule a bunch of them sequentially, and then come back at the end of the day and look at the results. I've been really interested in graph neural networks. So what graph neural networks are is essentially they're a network that works over graph-like data. So instead of having a sequence or an image, so a sequence would be, let's say, like a vector. An image would be like a tensor. But then a graph is also, like, if you look at it from an adjacency matrix point of view, like it is also just a 2D matrix. So the question is like, what kind of interesting algorithms can we make work on these? To learn some properties about this graph, like for example, like who are people likely to know each other. Let's say you're doing something with COVID contact tracing, like figuring out who could be sick. Other applications could be like on smaller graphs, like is this molecule toxic, yes or no. And so there's a bunch of different stuff you could do with these, but here's kind of where it gets interesting. So let me pull up the whiteboard here. So generally, like whenever we have discussions around like will this thing scale, it's typically like these are sort of the three knobs you can turn, like data, like model, data, or pipeline parallelism. And so, and if you're interested in any of these, I already have more than a couple of talks about them at this point. So, but if you have any questions, like feel free to interrupt me. So these are sort of three knobs that you can turn to make stuff fit. Like let's say it's something's too slow to train, then you would use data parallelism. Something doesn't fit, you would use model parallelism, or something is pipeline parallelism, as in, this sort of solves like the model parallelism data utilization problem, as in like different parts of your model are going to do different kinds of work and they'll end up being bottlenecked by each other. So why is this important for graphs? Well, turns out, well, let's say, if you're working with some molecule, for example, like with four atoms, then this is going to be a 4 by 4 matrix, right? Because like you can have like each one can be connected to itself, like or four others. And so but the point is that like even if you have like millions of these, uh, then you could still mini batch them and make them fit on any sort of device that you want. But this becomes a problem in this setting. So let's assume that instead of a molecule, you have something like a social network. So this now becomes, like a 7 billion by 7 billion matrix. Oh, okay. So this basically becomes a 7 billion by 7 billion matrix. And an interesting property of it, like, as you might imagine, is that this matrix would generally be very sparse because most people don't know most people in the world. Like, 0.00001% of people that, maybe, I don't know, 1,000 or 2,000 people if you're really popular. You're not going to know a couple of million. Like, that's just really unlikely. And so these matrices are going to be really sparse. So now let's assume, like in this case, like let's say what we want to do is we want to take these matrices, so let's just say this is the input graph, and we want to feed this to a GNN model. And from this, we either want to make a prediction or we want to make sorry, like, yeah, like a classification, or we want to do some sort of form of regression, or we want to do some sort of generation as well, like generate another graph. But this, like, as you can see, like this sort of becomes an issue. Like, well, when we're dealing with these 7 by 7 billion graphs, you can actually fit this onto the memory of a GPU. So, I mean, let me just show you here. So, for example, this is my GPU. I have a like 2880 Ti, which was you know top of the line before the 3080s came out. But it has about like you see here, like it has about 11 gigs. And so if I have a 7 by 7 billion, it's no way it's gonna fit. In fact, I do have a data set with about 100 million nodes and 1 billion edges. And that data set in of itself is about 50 gigabytes. So I'll talk about this for a second. So why is this a problem? Well, in the small atom case, like you could basically split any subsection of these and feed them, and then the total number that you would have at a time would easily be less than 11 gigs. Actually, your problem is trying to fit as much as possible so that you can keep the GPU's utilization high. That's why larger batches are good to a certain extent on GPUs. But in this case, like, well, you may ask, like, well, like, I want to split this graph, but then it's not really the same graph. And like, what if, like, and it does feel like you can't just like feed the same algorithm, is that you need to make your algorithm aware that the graph is actually split over multiple places. Uh, and so, long story short, like, there's no, because this is all complicated. Actually, if you look at the state of the art benchmarks on these things, so I'm gonna show you here the Open Graph benchmarks. So this data set that I was referring to earlier, the 100 million by 1 billion edges, this is an archive citation graph network. So basically each node is a paper and each edge is a citation. And so if you go to the benchmarks here and you go to the data sets, in this case, we're going to be doing some sort of graph prediction. So notice here that, where is it? Oh yeah, sorry. So this is a small graph case. So this is, let's say like molecules, for example. You notice there's like 430,000 molecules. Like they have at most like 26 nodes. So if you pad your matrix, then they're going to be at most 26 by 26. There's ways to not have to pad them with a representation called the disjoint union. But again, these are all solutions that work for small graphs, like not large ones. For large graphs, on the other hand, you're generally doing something like node prediction. So you'll notice here is that it doesn't actually say the number of graphs, well, because it's just there's one graph, but it's just one graph with 110 million nodes and about like 1.6 billion edges. And so, I mean, how do we do this, right? Like, so you would imagine, like, well, like maybe people have come up with distributed GPU learning techniques or whatever. It turns out, like, if you actually look at the leaderboard for this, uh, all of the leaderboards are using a CPU. So they're using this guy, like the Xeon. I think this is a pretty expensive CPU, to be fair. Let's just check it out. Yeah, it's a $10,000 CPU, 28 core, 2.5 gigahertz. Wait, how much is mine? Wait, so is my thing better than this? That's nuts. Oh, this is something else. Okay, but regardless, like my point is that they're all working with CPUs that have a large number of cores and have a ton of RAM. That way, you can just fit the entire data set in RAM and not have to worry about it. But this sucks, right? Because if all we're doing is you know, so basically, I've talked. I sort of touched on this in my the hardware lottery talk I gave. But the reason this sucks is because our GNN algorithm, like this is just a sequence of matrix multiplies. And the reason this sucks is because while like and what's sort of important about matrix multiplication is that you can speed it up with more cores in general, right? So let's take a look at like a top of the line CPU is gonna have something like, let's say like 32 cores. Like for example, mine is 16, for instance. So this is like what you would expect at like some data center, or, you're doing some sort of cloud training or whatever, or you're just like doing lots of video editing and you would buy this. But GPUs have like an order of magnitude more. So like let's go back to Task Manager. I think it shows up here. Okay, so it doesn't show up, but if I recall correctly, like the 2080 Ti had about like 4,500 cores. And then if you look at the 3080, then I think that was closer to 10K cores. And so if we can speed up these algorithms like linearly in the number of cores, we really want to run it on a GPU. But it's not really obvious how we can run it on a GPU given that we're constrained by the on-device memory of about like let's say 11 to I don't know 17 gigs at the most. So okay, so this is sort of the problem definition. Like, you know, ideally we would want to run this on a GPU. It would run a lot faster. We can't, it can't fit. So we default to CPUs. So I'm going to be asking, you know, so sort of like we're going to be doing two things. Like the first thing I want to be doing is I want to show you a GNN library that I've already covered before called Spectral. And Spectral is really interesting because it's a TensorFlow library with minimal bindings on top of Keras. Like it just turns it into a data pre-processing step, like dealing with graphs, which I really like. And so if anything you'd expect to run fast with Keras on any sort of GPU, you should expect to run fast on Spectral. This is very powerful. There's basically, you're relying on perf improvements lower down the stack. And the second thing I want to cover is an algorithm called cluster graph convolutional network. And so basically this algorithm, like I mean, I haven't read the paper yet, but the main idea is that like, let's say if you have a graph with 7 billion to 7 billion, can you turn this, for example, into something like, I don't know, 100 million, 100 million, you know, with some clusters as opposed to nodes. So this is nodes and this is clusters, and still be able to do a reasonable amount of predictions and get reasonable results. So how'd this sort of come about? Like, I mean, this whole discussion and all of my thoughts around this sort of started with this like GitHub issue. So basically, let me pour myself some coffee. This may be, I don't know how long the stream today will be, but let's see how it goes. Okay. So as you can see here, like, so I came in and this was on the Open Graph benchmark repo. It's getting more popular, has about 600 stars. And what I was asking was like, okay, well, I want to run the spectral code, which, you know, does some GNN on some proteins. So like, I want to take the exact same code. Like maybe I'll need to make the model better, like bigger to make the accuracy a bit better, like actually get it to converge. However, it's not really obvious how to do that. So what, like, I ran into this issue because I had provisioned an AWS cluster with about like 350 gigs of disk and 32 gigs of RAM, and it kept running out of memory. And I was confused, like, oh, like, couldn't it just like cache the different parts of the data set that it needs? Turns out, no. Like, I mean, turns out I need to think about this a bit more carefully. Like, you can't just allocate a NumPy array. Like, I need to do something with streaming, or, you know, even with streaming, it's not obvious what to do. So I just thought I'd ask the maintainers. So just to show you the original code here. So basically here you come in, this is just like some basic evaluation scripts, like, you know, very traditional stuff. And so you come in here and you're like, okay, I want to load this data set called, for example, OBGN archive data set. And so you load this data set and then you say, okay, well, it's some sort of node prediction task. And this is important because, why is this not autocompleting? Wait, GitHub, Octet, GitHub source code navigation. I thought I had it. I had this on. Okay, looks like it's built everywhere. Okay, so what I just wanted to show you was that if you actually look at this node prediction data set, it inherits from another data set called like an in-memory database. What that means is, you know, if it's big, it means you need a lot of RAM. So we could, you know, go back to the Stanford data, so the OGB repo, and change this and actually make it work better. But this is sort of like the logic here. So we take this thing and then we turn it into some sort of NumPy array. Once we feed it as a NumPy array, we do this like test and train split. And then we do like a very traditional, like so you'll see like this looks very similar to what you would do with a regular convolutional network, but instead of a convolution, it's called a graph convolution. But they're sort of similar. Like you have the normalization, you have dropout. So all these operations mean something slightly different, but within the than what they mean in images. But within the context of graphs, like the way you should think about it is, if you're trying to learn some property about the node based on the entire graph, you can do the equivalent of a convolution operation, where convolution in this setting, as opposed to your neighbors in pixel space, means your neighbors in graph space, as in like your neighbors, like who are the edges, like who are the nodes that you're connected to, like those are the features from which you'll inherit the most. So once this is set up, you just have a model. You say, I want to learn by atom. I want to compile the model with sparse categorical entropy, and then I just like want to print out like accuracy and a bunch of these metrics. So this is an issue, like I said, because of this line. This line. Once you do this, you're gonna run out of memory, and even I would bet like this would just straight up run out of memory, because I'm assuming this is just doing the same thing. But when I mentioned this, well, first off, they said, first make sure that you're using a machine with lots of RAM. Like they didn't say do anything with streaming yet. So I was like, okay, great. But then I was like, wait, what do you mean? Make it fit? Like, what if I don't run this on a GPU? It doesn't really fit, and I don't know really how to do model or data or pipeline parallelism in this case. So Chili replied, well, you actually, like, you can theoretically do it with some algorithms like cluster graph convolution networks or graph saint. So they increase computational time. In addition, at inference, you probably still need to go back to CPU, because even if you compress it for training, when you're actually trying to come up with the results, you're gonna still need this whole thing on CPU. And so it depends, like, right? Like, did you want, like, yeah, you could speed up training, you're not going to speed up inference. This is sort of like an unfortunate side effect of working with these models. So I thanked Chile. I said this is super helpful. And then he got back to me with this repo that I wanted to check out. And so this is a repo, and it uses it uses this. We'll sort of go through the paper here, because I don't think the code will make too much sense if we just go through it as is here. But so this is gonna be our agenda today. I want to go over the spectral paper, figure out like how does spectral really work, and I also like spectral because I really like Daniele. So he's just in general been super helpful. Like whenever I have any questions about any of this, he's super responsive in all time zones. I think he's a PhD student in Italy, and so just generally made my life a lot easier. And in general, like I think that while PyTorch geometric is more popular, like I think it's about 9 times more popular on GitHub, just in terms of star count. I don't know what that translates into real commercial use cases. Uh, Fundamentally, like I feel like PyTorch is a great prototyping language, but it just comes like at a huge it just gives you a huge perfect when you're running something. And in this particular case, where you're running over these gigantic graphs, like this is where this really matters. Like if you're inching in like 2x perf, 1.5x perf, like that's the difference between like waiting 2 days for a model versus one day. It's the difference between like full day versus half a day. So it really matters. So for me, because I really am viewing this as in it's important for me to have good perf, like that's why I'm using Spectral. So, yeah, like without like this was I guess a lot of introduction. So let's just like without further ado, like we can just start with the Daniele paper. All right. So okay, so they're saying basically, so this is his I believe this is his advisor, so he runs the lab in Italy. Uh I think it's between Italy and Switzerland, if I'm not mistaken. Like I remember that the area just generally has good machine learning talent. So they're saying he presents Spectral, an open source library for building graph neural networks, and implements a large methods for deep learning on graphs, including message passing and pooling operators, as well as utilities for processing graphs and loading popular benchmark datasets. So it's to provide essential building blocks for quick prototyping. It's suitable for absolute beginners and experts. We present as an overview of Spectral's features for node classification, graph classification, and graph regression. Interesting. Okay. So in case I haven't mentioned any of these, like node classification would be, let's say, does this person have COVID in a social network? Graph classification would be, is this molecule toxic? Yes or no? Graph regression could be, how photovoltaic is this molecule? So like on a scale of 0 to 1. So GNNs have been used to learn physical methods of complex like particle systems. Okay, I've seen this paper before, but and get they use them in recommender systems, new potential edges. Battaglia, I mean, let me look at this paper. To everyone in chat, just like feel free to ask me absolutely anything you like. Okay, well, this is loading. It's gonna getting my laptop charger. It's interesting. This page took forever to load. This is a gigantic paper. So relational inductive biases, deep learning, and graph networks. And this came out 2018. Okay, interesting. Okay, Chomsky. I mean, this is like relational reasoning. Oh, I see. Oh, interesting. Like, I think this is just a good survey of GNNs overall. Interesting. Maybe I'll do this in some other lecture because I think this will be helpful to understand the. This looks really comprehensive. This looks great. Oh, they have GraphNet. I wonder though, like, do I have this started? I do have this started. Aha, past mark. Um, what I'm curious is that, like, let's look at Sonnet. Okay, so it looks like, if I'm not mistaken, Sonnet looks like just plain like there's some libraries on top of plain TensorFlow. So if you support TensorFlow, you would support Sonnet out of the box. Do you have examples? Oh, I see. It has a very PyTorch vibe to it, right? Feels super similar. Like almost with the letter, right? Like, okay, here's the module, here's the layers on top, and then yeah, chain them into each other. Well, what happened to Sonnet? Because like it's like I guess now it's all about jacks, if I'm not mistaken at Google. Okay. In all cases, like this doesn't matter too much, I think. And so what we'll do. Okay, yeah, sorry, I got distracted. I am gonna download this paper, and then what was it called? Inductive biases. So relational bias, inductive. Okay, amazing. Oh wow, so many people in chat. Well, hey everyone. So if you have absolutely any questions, like feel free to ask me. I'm happy to explain anything. Uh, I'm mostly going to be talking about GNNs today, but I'm happy to talk about anything else that's somewhat related. So they've also been applied to the biological science, ranging from recommendation of medications to the prediction of protein-protein ligand interactions, for the prediction of quantum molecular properties, as well as the novels of compounds and drugs. And they've applied in fields like NLP and even more abstract tasks like, oh wow, this is actually a really nice like survey. So basically, I mean, I'm just gonna say this, like it's just used everywhere, right? And so at the core of the GNNs are two types of operations that can be interpreted as a generalization of the convolution and pooling operations. So we have message passing and we have graph pooling. So the former is used to learn a nonlinear transformation of the input graphs and the latter to reduce their size. So when combined, these two operations enable graph representation learning as a general tool to predict node level, edge level. Uh, wow, okay. This is a huge literature. So thanks to the increasing popularity of GNNs, there's been many libraries. Not in benefit, cares an application programming interface for creating neural networks. That being able to go from idea to result with the least possible delay is key to doing good research. Oh yeah, I was more sort of making a similar point with like my DevOps commentary earlier. But yeah, so let's look at how they're defined. Like I think I've talked about most of this before, but let's see how they define it here. So the role of message passing is to compute a representation of each node in the graph, leveraging local information from its neighbors. Right. Okay. So you can think of like each node as its own server. So have like imagine like a sort of like vertex model where each node is gonna say like I want to know what my representation is, and then that node is gonna ask all of its neighbors for what is your representation, and then it's gonna use it to aggregate it. So at the simplest level, you can imagine like let's say each of your nodes, each of your neighbors has like some. Actually, maybe let me do it on the whiteboard. I think it'll be simpler. Let's see. Is to reduce the size of the graph by aggregating or discarding redundant information so that the GNN can learn a hierarchical representation of the input data. Global pooling layers reduce the graph to a single vector, usually to feed it as input to a multi-layer perceptron for a classification or regression. Okay, sure. So let's go here. So we basically, well, first thing is, we have this, let's say we have this node, right? And this node basically, like, let's say they each have a feature where, like, let's say that there's node features. So let's say its value is 1. Sorry, actually, let's say value unknown. Arg. Okay. So let's say here the value is unknown, but we know that here, like, this person has COVID. We know that this person has COVID. And, we know that this other person doesn't have COVID. And then, for example, we could have like another edge weight, which is like let's say the frequent, like the number of times they've interacted with each other. So this could be like they've interacted with each other a lot. Then this is like they interacted with each other like 10 times, and then this is 20 times. So I'm not saying this is the best model, but one reasonable way to predict whether this person has COVID is you could say, well, I want to take the sum of the edge weight times the vertex I for all I in neighbors of node. Right. So what this works out to is it could be something like, well, 1 times 20 plus, oh, sorry, like let's say divided by sum of EI. Right. So then this is going to be 1 times 20 plus 10 times 1 plus 50 times 0 over 20 plus 10 plus 50, 30, so it's 80. This is going to be equal to 20 plus 10 plus 50 divided by 80. And then, like this is 30, 80 by 80. And then this is like a model saying like, yes, indeed, this person has COVID. Again, this is not a great model because it actually, oh wait, sorry, this is 0. Sorry. So this is gonna be like 30 times 80, which is less than 0.5% chance that this person has COVID. And so this is not a great model, right? Because uh, actually, no, it could be a reasonable model, right? Like let's say if the number of interactions turns out wasn't all that frequent, it's 10 or 20. So basically, like my point here is that this whole thing is called message passing. Like this idea of each node doing it the other another, because this is just like a single node, right? But every node is going to do this. So then this node is going to do the same thing here. It may also aggregate its own local information. And then so you're going to keep doing this, and then you're going to end up having some values. But then you want to turn this into just like a vector that you can pass into GNN, that you made in Keras. So then this would be the pooling part. So we're gonna talk about this next, but that's sort of the basics of the message passing idea. So you'll see here, for example, in the message passing, well, the reason you sort of need to pool is because, well, when it comes here, like ideally, I also want to know if this person was like, let's say this person was, 1,000 times in contact with this person that we know they had COVID for sure. Like I want a sort of way to represent this information. So one way to do it could be like you have like a direct edge, so from everyone to everyone. But here you end up with the other case where you end up with a 7 billion times 7 billion graph. And instead, what you want to do is you want to sort of aggregate this by neighborhood. So you want to, for example, say that this is one neighborhood, and then this is another, and all their neighbors, and then this is a third neighborhood. So this is called like so. Really, this is how pooling works, right? So you do this pooling. It gives you a representation, and then you GNN, and you're pretty much good to go at that point. Uh, so yeah, I mean, obviously, I think all of this stuff is sort of easier said than done because it's like, well, what do you mean by message passing? Like, what do you mean by vertex centric? Oh, this pooling is complicated. Oh, what about concurrency and scheduling? That's why it's good to use someone else's library. Like, like you can use something like MPI. That said, if you are interested in how some of this stuff works under the hood, uh, I would say like the best reference that I found to just like kind of understand systems from a scientist perspective was Chris Rakakos's new course on YouTube on parallel and scientific machine learning. Like his last lecture on the different models of parallelism, I thought was exceptional, and it sort of explains a lot of these ideas and trade-offs and how to think about them. Okay, so all the features of spectral are documented in detail. It's the MIT license. Okay, yeah. So you have a graph, and then each graph. Okay, so what's sort of interesting about this use case is that, well, we sort of took the simplest use case, which is each node is represented by a single feature, right? And then each edge is represented by a single feature. But both of these could be vectors, and it could be vectors of vectors. So like you could just have like, this monstrously complex data structure that represent each node, and it should still work just fine in this case. All right. So another thing is that, like, well, we talked about this, is that all of this is very sparse. And so this works really well with the sparse matrix libraries in SciPy. So what they do there is they use a format called the COOL format. The way this format works, uh, I mean, like I'll just cover the algorithm for you because I think it's sort of interesting. I'll just write it here quickly. Um, so let's say you have two vectors, like you have vector A and then you have vector B, right? And then so this is A1, A2. Uh, I'm just gonna end it at AN, let's say, and then this is B1, B2, BN. But let's assume that this is just gonna be. I mean, oh wow, let me zoom in. Okay, so the way you would usually do this is you would say something like for AI in A, and then for BI in B. Then you have like, let's say something like result, equals 0, and then you would say something like, uh, actually no, let's do just the vector. So like result is this, and then you would say result dot append AI plus BI, right? So this is sort of the traditional way you would just sum up a vector. Or let's say you're doing just like dot-wise product, or whatever. Even if you're reducing it, still same idea. So what I want to show you is like, well, like what does it mean for this to be sparse, right? Like let's imagine now that this thing is like I put n because I want you to imagine this is like a million by, this is like a vector of length a million or 10 billion or whatever. It's just absolutely massive. So what's going to happen in these loops is you're going to go through the whole thing, and then you're going to go through the whole thing in B, and then you're going to do this, and then you're going to do this addition. Instead, you can imagine that, like, well, what if, uh, like, instead of working with vectors as matrices, you could work with them as vectors. So, for example, you could say like A is equal to A1, A2. Sorry, like let's say this is A, like this is A, and then this is B. And instead of putting in every single value, so basically all the indices from 0 to n, you would only have values for the keys that you care about. So basically this would be look like this. Like it'd be A, like let's say A1, but turns out like A2 is 0, so then it has like AN, sorry, it has N, and then this is AN. Notice like the like let's say A2, and this is because A2 is equal to 0. So in this case, like because this is sparse, like because you don't even have it, if you're iterating over the elements of A, that means that you're just simply gonna skip all, like you're gonna only look at the elements that you actually need to. But this gets even better, right? Because like you're gonna be doing the same thing with the B, right? So then let's say now this is gonna be, it's gonna be 2 and then B2. And then it's gonna say something like n and then bn. So really what this is saying is that we want to have 0 for everything, except for the very last one. That's when we need to add them. So basically you say something like if, so for, let's say keys in, uh, like basically key val in enumerate of A. So basically only go over the ones that you need. If key in B, then you say, let's say result, and this is again a dictionary. You'd say result of key equals, actually, yeah, so we also need the value. So yeah, so we would say like val of, val of B plus, like, yeah, in this case, I'm gonna do something like this, right? This is just abusing notation slightly. But this is sort of the main idea, is that like like if you just represent vectors as a dictionary, you can just skip computations you don't want to do. So when people talk about sparse libraries, like it sounds like very complicated, but this is sort of the core idea that what people do there. So yeah, that was a digression. I hope it was useful. But anyway, we can get back to the main paper. So you can see here, for example, is that in spectral we represent G. So G is the graph as an adjacency matrix n by n, right? And then node features, which are n by f. So each node is going to have f features, right? Yeah. And then edge features, which are the set of edges. Okay, yeah. So n by s, yes. Well, because you have n squared edges, right? You have n, if you have n vectors, then you have n squared possible edges, like all possible connections. And if each of these edges has s possible features, then the total size of this entire data structure is n by s. So it's really interesting about all of this stuff is that, well, because you're sort of working with, you're working with, I'm gonna say, like, let's say, like you have a matrix A, which is the agency matrix. And then let's say you have some matrix V, which is the node features. Then you have E, which is the edge features. So typically this is interesting, well, because in typical machine learning, like let's say in images or languages, you feed your data set as like one matrix, then you feed it to like let's say like your like DNN, like say KRS, for example. But in this case, you're actually feeding all three. Like you're feeding all of these to KRS. And so this is where like the functional API comes in, and it's like an API I personally really, really love. Like it's just like you can come up with all sorts of cool ideas, like combine features from different sources. And this is just like one application where you wouldn't even be able, it wouldn't necessarily be even possible to do it, at least not easily without the functional API. All right. So they're saying, first of all, message passing are a general paradigm introduced by Gilmer that unifies most GNN methods found in literature and a combination of message aggregation and update functions. So message passing layers are equivalent in role to the convolutional operations, and they're in spectral. They're available in the layers convolutional module. And they implement 15 different message passing layers, including graph convolutional networks from Kipf and Welling. Oh, I follow Kipf on Twitter. He always publishes interesting stuff. But they have a lot of stuff, like they have Shebnets, Graph Sage, ARMA convolutions, graph attention networks. Oh, I see it. Figure out which nodes should you attend to. Graph isomorphism networks, as well as methods proposed by Liu al. Okay, great. So I'm just gonna quickly. I also follow. Well, is this Maxwelling from Qualcomm? Oh, this is cool. Like they made a blog post to accompany the paper. Yeah, it is Maxwelling. Okay, so this is all gonna, we're gonna cover all of these later. And so then I'm also interested in Graph Sage. Oh, I see. Oh, interesting. Okay. So basically, Graph Sage is like dimension reduction for nodes in a GNN. So this doesn't necessarily solve, actually, you notice like this doesn't really solve the problem, the original problem we had. Oh wait, why is this charger not working? Okay. So this doesn't solve the problem we had. Like our problem was still is just like, even if it was just a bit byte or whatever, like it would just, you're not gonna fit this into memory. And of course, but it gets worse, right? Because it's more of it's an additive cost, whereas then increasing the number of vertices in the graph is a quadratic cost, because it's yeah, because you're basically going in both ways in the adjacency matrix. So what about graph pooling? So it refers to any operation to reduce the number of nodes in a graph and has a similar rule to pooling in traditional convolutional neural networks for learning hierarchical representations. So because pooling computes a coarser version of the graph, it results in a single vector representation. It is usually applied to problems of graph level inference. So graph pooling layers are available in layers pooling, and they include diff pool, min-cut pooling, self-attention graph pooling. And it also implements global graph pooling, which can be seen as a limit case of graph pooling where a graph is reduced to a single node. Oh yeah, so this is what I was talking about, right? Like if you're pooling stuff from your neighbors, so I had this here. Like this was sort of a sort of mechanism we can make up, right? Uh, but if you go back here, you'll notice like, well, you could take the sum, you could take the average among your neighbors, you could take the max. Like let's say within the case of COVID, maybe max makes more sense, because if you do interact with one person a lot, it doesn't matter if everyone else doesn't have it. So that's where a max may make more sense. Uh, some could be something like, well, I don't know, like how much do you exercise? And if, on average, all of your friends exercise, maybe that matters more than if one of your friends is really into exercise. This is like all like very hand wavy, but you could imagine that depending on what you're trying to predict, different pooling strategies will be better suited for that use case. I think this needs some like just domain knowledge. So the data sets that they use, like what I thought was what I thought was interesting was they really had a lot in spectral. Like they had all the open graph benchmark data sets, like the benchmark data sets for graph kernels, and it's downloaded and stored locally when necessary. Yeah, that's right. So the way this works is Then has made it really trivial. Like you just literally say, I want this data set, load as an NumPy array, and then you're good to go. And it just downloads it locally for you. And if it doesn't exist locally, then it'll create a directory, put it in a data folder. So it's just like sort of like nice quality of life things, which I think are usually indicative of people that plan to support libraries and make people's experience better, as opposed to just like the more hackier scripts that I, for example, write. Um, so while the NP and pooling can increase the number of different message passing and pooling layers implemented by the library respectively. So it looks like PyTorch geometric uh, implements the most in general. So it's cool that he's aware of that. But I guess like again, like this sort of becomes relevant, like especially for inference and for people looking for high performance compute. They may not want the overhead of PyTorch. Like maybe experimenting with it initially is cool, but honestly, I found experimenting with Spectral to be like a joy. It's just so easy. Like I just change two little things and change the data set, and it works. Um, and so so they also added like a layer and ops modules, which lets you like extend it. So okay, great. So the most notable resource is PyTorch Geometric and the DeepGraph library, which are based on PyTorch deep learning. It's estimated to support the majority of deep learning applications, both in research and industry. So they're summarized in label, implementation details, spectral applications. Great. So in our first, we consider a task of semi-supervised node classification on Quora. They take graph classification, and then results are sometimes different from what is reported in the literature. Min cut, diff pool, top K. So starting the message passing information. Streamlined user experience and is currently the most mature library for GNNs in the TensorFlow ecosystem. In the future, we'll keep Spectral up to date with the ever-growing field of GNN research, and we will focus on improving the performance of its core component. Okay, so for me, the big thing that uh, single mode. It's talking in a higher tensor shape. Oh, interesting. Okay, yeah. Let me just summarize some of this paragraph for you. I think it's important. So, so they mentioned this in the docs, but like I'll just wow, I have space here. Excellent. But in general, like when you think of it, is well, like let's say you have one small graph, right? The utilization, like let's say this is small, then utilization on a GPU will be low. Because remember your GPU has thousands of cores and wants to keep everyone occupied. So if you just give it like this 4x4 atom, like it's not going to do much work, and you're probably not going to get any benefits from a GPU because you're going to need to load it via PCIe, get the result back. So you might as well just do your experiments on a GPU. So another way to do it is that what you can do is you can take various matrices, and even if they have like different sizes, you can stack them in this like diagonal format, and then feed this whole thing to a GPU. So this representation is called the disjoint union, right? And it's good because it's sparse. Like part of its issue with on a GPU is that this representation ends up being very sparse. Uh, but at the same time, no padding is needed. And a final way to do it is instead of feeding everything like this in this diagonal format, you could do what people typically do in deep learning, which is that they will take they would uh, so you basically just stack all the matrices in like this like very large tensor, and then you feed it in a GPU. So this is called batch mode. The issue with batch mode, though, is that because, uh, like, if you're stacking matrices on top of each other, they need to be of the same dimensions. So you need padding, which can be a problem because let's say most of your matrices are size 4 by 4, but then one of them is size 16 by 16. Now all of them need to be size 16 by 16, or you just remove it from the data set, or just not do a prediction on it. All right. So unless anyone has any questions, I think I actually want to move to the graph like so the graph clustering algorithms on top of the graph convolution algorithm. So let's just do that. This is a good paper, like so understated. Yeah, hey Pseudomaze. It's nice to see you. I had to miss like stream last week. I was out traveling, so I sort of needed the break, so I just didn't really feel like streaming at all while I was on vacation. But yeah, we're back at it now. Let me know if you have any questions about this paper. It's an amazing paper. Otherwise, I'm gonna move on to like just graph convolutional networks at this point. Interesting. So this is like fancy researchers like Google Research, Sam Bengio and stuff. Brian Liu, Wei Li Ching. Wei Li Chang. That's not the Wei Li Chang I want. I think this is it. I also think this is not the National Tsinghua. No. Oh, it's Lin. Right. Uh, okay, so it looks like this is his. I mean, I don't know if it's him. It looks like it's their most important paper. Microsoft Asia, Google Research. Okay, very fancy profile. Oh yeah, I also have software for it. That's cool. But yeah, like this is the Logitech Brio. Here, I can even show you. It's like if I do this, and so this is Logitech Brio, and then this is like the background as well. The camera is just overall like way better. Like it's I think the other ones look like a potato. I also got a fancy mic. I got like the Blue Yeti. They make all the difference. Just really good stuff. I had a green screen. It's pretty much useless now. It's just you know under my bed. I forgot to return it. I think Jensen made my green screen obsolete. Okay, how long is this paper? 10 pages. Okay, great. Not huge. So I think I'm going to cover this paper and probably call it with the conclusions. I've been rambling for a long time. So graph convolution networks have been successfully applied to many graph-based applications. However, training large-scale GNNs remains challenging. So current SGD-based algorithms either suffer from a high dimensional cost that exponentially grows with the number of graph convolution layers, or a large space for keeping the entire graph and the embedding of each node in memory. Okay, so this is actually the main problem I was interested in looking at today. So this is, like here. This is why we're here, boys. Uh, so in this paper, we propose cluster CGN. So it's a novel algorithm that is suitable for SGD-based training by exploiting the graph clustering structure. And at each step, it samples a block of node that associates with a dense subgraph identified by a graph clustering algorithm. It samples a block of nodes that associates with a dense subgraph identified by a graph clustering algorithm. Okay. And restricts the neighborhood search within this subgraph. This simple but effective strategy leads to significantly improved memory and computational efficiency while being able to achieve comparable test accuracy of previous algorithms. To test the scalability of our algorithm, we create a new Amazon 2 million data. Third author, CC. CC. Uh, with 2 million nodes and 61 million edges, uh, with 2 million nodes and 61 million edges. Oh, that's way smaller than what I'm looking at. Like I'm looking at 100 million nodes with a billion edges. Did I just like bite off more than I could chew? I was like laughing at this point. Okay, this is way smaller than what I've tried. It's like not very big. Okay, XD. So let's just keep going. So for training a 4-layer GCN on this data, our algorithm can finish in around 36 minutes, while all existing algorithms fail trained due to out-of-memory issue. So it allows us to train much deeper without much time and memory overhead, which leads to improved prediction accuracy. Using a 5-layer, we achieve state-of-the-art on the PPI dataset, while the previous best result was 98.16. And our code is publicly available here. So what's the PPI dataset? Oh, I see. It's a protein dataset. All right. So graph convolutional neural networks have become increasingly popular. No, sure. They're super great. Okay. We first discussed the pros and cons of existing approaches in terms of memory requirement, times per epoch, and convergence per epoch. So these three factors are crucial for evaluating a training algorithm. Note that memory requirement directly restricts the scalability of algorithm, and the latter two factors combined together will determine the training speed. Big O and N times F times L. Oh, I like this actually. Oh, interesting. Okay. I see the point here. So, I mean, they're saying it in a complicated way, but I think this is how I would summarize it. So basically, imagine that you're not doing any sort of pooling or anything like that. Like you just have everything's fully connected, fully connected graph is big O of NFL memory. So this means you're going to run into out of memory issues. But if you want to sort of pool them, then pooling takes uh, exponential time and number of nodes. So it's also not a real fix. Like you're almost trading off like memory and time. Uh, I would say for the most part, memory is cheaper than time. Like you just, I don't know, get like 1,000 terabyte, like I don't know, like a 1 terabyte RAM machine, you know, machine for the win, and then you're just good to go. Because your time is actually more valuable than machine time for the most part, unless it's just sitting there doing nothing, and it gets really expensive. So they propose to use a variance reduction technique to reduce the size of neighborhood sampling. Uh, and it requires storing all the intermediate embeddings of all nodes in memory, leading to this much memory requirements. So they propose a novel algorithm. Then you are, unless you are the machine, then you're pretty much like, I mean, you're just, it's like being, it's like sort of like, I mean, I definitely pity the machines doing crypto mining. It's sort of like, they don't have a fun life, you know? It's like 100% utilization until you die, until you burn in flames. Yeah, it's like the poor DGX, exactly. So based on we propose cluster CGN to design the batches based on efficient graph clustering algorithms. And then we take this idea further by proposing a stochastic. Wait, so first off, 2 million nodes, Amazon to M data. Oh, interesting. Free range GPU ban caged farming. Oh my god. Yeah, I don't know. um, yeah, we'll see how it'll work out. Like, maybe we should be like, kinder on our GPUs. Like, it's like do crypto like 90% of the time, but then it's okay. You can play Cyberpunk once in a while. I mean, it's gonna get worse. I like imagine like if you move to a world with like server based gaming, which I mean I don't know if it's gonna happen at this point or not. But if you do, then yeah, like those poor machines are gonna have 100% utilization. At the very least, in my case, like when I sleep, like my poor machine's generally not doing much. My servers at work, on the other hand, like poor thing, But my, my 2080 Ti is much more precious. All right, so it's proposed background. Hey, I'm Horace. Oh, hey, Horace. Like, it's really nice to see you in chat. Yeah, so everyone like Horace was the one to introduce me to this paper. So I asked him the question on GitHub. So for me, this has been pretty cool because like I'm sort of trying to figure out like how to speed this stuff up at work, and I sort of did the silly thing where I just provisioned an expensive AWS machine, and it just kept running out of memory, and I'm like, what the hell's going on? Um, so I will say like Horace, what I thought was funny by the way about this paper is that if you look at this, like they're saying that they're working with 2 million nodes and 61 million edges, whereas the archive data set is 100 million nodes with a billion edges. So I just think like because it's sort of orders of magnitude more, like I don't know really how this is gonna work out. But sort of like maybe since you're here, like I'll give you a sort of conceptual way. I need to read the rest of this paper at this point, but um, it's almost like I had this interesting discussion with someone who works at Tiger Graph. So Tiger Graph is an in-memory database for graphs in general. So generally, they recommend their customers like, look, just get like I don't know, a terabyte of RAM machine, and then just like run all of your BI processing on top of it. But given that, like, let's say if you're a huge company, that may not fit. So then they have the solution where they can cache some of your data set on disk, and then you just load in what you need when you need it. So I'm not really sure how this would work for this, but what I was sort of thinking is like sort of like an ideal API is like imagine where you have a data set and then this is like a matrix, and this is like a NumPy matrix, and then what you do is you basically let's say something like A and then Tiger Graph A, and then basically just feed in this to like spectral or torch geometric, and then just give it A, and sort of like trick the GNN libraries into thinking this is just like one contiguous matrix, but just have the matrix sort of intelligently stream in what you need to do. But this sort of, to me sort of gets interesting because generally I don't know anyone who thinks about this, at least within the ML community. Like, I mean, I think in the BI community, people have thought about this because they need to think of ways to stream data in. But generally, like what's sort of, I mean, like I don't know if you look at even like sort of the map reduce setting, is you have the stream of data coming in, like sure, but then you're always doing this like super elementary operation on each one and reducing. You're not doing this sort of complicated thing where you're going through the past of a stream. Like, so do you need to run on papers 100 million size data sets and then like streaming really large graphs? Uh, yeah, so kind of like I mean, so the streaming part is just me sort of hand waving, thinking about how this could potentially work with the right infra. But in general, yeah, I will say that I think, do you need graph neural networks for your problem? Yeah, pretty much. So I mean, I'll give you sort of the motivating example even. So imagine you have something like, you're doing something like COVID contact tracing, right? And so this graph, like let's say it's just limited to the US, is going to be a graph with 300 by 300 million nodes, and then each node, like a person, would have very dense features. Like it will be like, let's say, all of their historical records, their symptoms. Edge level features could be something like, have they met? And then you're trying to predict like, how likely is this person to have COVID? Uh, and so this is sort of like the conceptual framework. And so just like full disclosure, by the way, like I work at a company called GraphCore where we have our own hardware called an IPU. So because like I had trouble figuring out how to fit this on a GPU, I'm sort of now figuring out, well, okay, is there also potentially, is this like a hardware limitation thing where it's like, well, maybe the IPU would be better, or is it just like more of a RAM thing? Is it like a streaming memory thing and it would work regardless? Uh, I'm just starting to think about this stuff now because for the most part, when I've been thinking about graphs personally, I generally think of them in the setting as I have a small graph, like a molecule, and I do a prediction. And if it's if it doesn't fit, like it's gonna fit because I could always do model or data or pipeline parallelism, and that's all fine and good. Like those are all things I understand and use a lot at work. But this is sort of new territory for me, so I'm still slowly thinking. So I was actually super grateful for your like patient answers on the GitHub issue. So really, thank you. All right, so sort of like moving on. So you have an n layer GCN, and it consists of an L graph convolution. Each of them constructs embeddings for each node by mixing the embeddings of the node's neighbors. From You might want to check this paper out. Simple scalable graphical neural networks. Is this Michael Bronstein? I'm gonna bet it's a Michael Bronstein paper. Yes, I guessed it. Dude, the guy writes all the blog posts about like GNNs that I found. Like, I haven't found a single person talking about GNNs on Medium that wasn't him. Um, I should reach out to him and ask him for his thoughts as well, I think. Still open question whether depth is needed. Oh, interesting. A general probabilistic graph sampler clustering the, but he kind of summarizes what the problems are. Yeah, that's what I sort of like about him is that like he has dense papers, but then also does a good job of summarizing what's going on. Was Graph Sage. So they use neighborhood samplings combined with mini batch training to train GNNs. Actually, you know what? I'm just gonna read this instead. I think this is more helpful than the full paper. I'll just skim it just so no one gets upset at me. The proposed algorithm. Okay, sure. So how did they get the clusters in the first place? We partition its nodes into groups where they consist of the nose and teeth partition. For the semi-supervised node classification task, I think it's an open question whether graph neural networks are really needed, lol. Um, I mean, like, I would actually argue, like, uh, I don't know, like, there's like a meme at this point, but I would like, I fully expect like ML to just dial back to fully connected neural networks at some points once people figure out some better optimization algorithm than backprop. Uh, but otherwise, I mean, yes. So you're really saying is that like in this case, you could just do some like node level aggregation and then just be done with it. That you don't need any sort of more global features. Is that what you mean by we don't need GNNs? So only requires computing BL embeddings, which is linear cluster. Stochastic multiple partitions, nodes together. Okay, fine. Yeah, this is what I wanted. So randomly choose K clusters without replacements. So form the subgraph G with nodes blah and then links blah. Compute the loss on the subgraph and conduct Adam update using gradient estimator. What is this loss on? Loss on subgraph. Are they just computing an optimal partitioning? Is this what's going on? What's the main contribution? So Michael Bronstein's paper SIGIN, which is basically just another version of an early paper simplifying graph convolutional networks, essentially just computes pre-processed features. Oh, interesting. And so I see. And so sort of what like this is sort of I think an interesting point because let me just maybe let me do this. I just want to write this for myself because I think this is helpful. So the reason I think this is interesting is because if this is what you're doing, then basically there is no like, like no training time, but then you want like high throughput to be able like basically so I think it's what you said earlier as well in the GitHub issue where like you still need the thing to be uh I mean, yeah, because like if you're just computing local pre-processed features, it's just like you're doing, I don't know. Like so by the way, when you say pre-processed features, like is there still a matmul involved at this point, or is it like I'm guessing it's just like some form of pooling and aggregation, and then you just spit it out just based on local features without looking at anything else. I see. Interesting. Yeah, like I mean, yeah, so this is I'm gonna say this and then Horace. Like not clear if you need GNN for edge node features for large graphs. Oh, I see. So it's basically yeah. Okay, that makes sense. Like it, but it's a matrix multiplication with both where both matrices are small, or at least the size of. No, actually, it's not small because it's like all of your neighbors, right? Or oh, but it doesn't matter because you don't need to stack anything or do anything like that for training because you don't need the batch data. You just do this tiny matrix multiplication. Yeah, it's not small. Okay, got it, got it. Okay, so let's do this. So cluster CGN. So what did they say their main contribution was again? So they're like, we can at least improve prediction accuracy, which is state of the art. F1 score, while the previous best result was this. Okay. And then let's go back to the algorithm. Random partition, cluster partition. Oh, interesting. Okay, so this is sort of how, but you don't need to do it during training. You can just do it once as a pre-processing step. Yeah, that makes sense. Well, like it's just a single operation. There's no forward and back prop, and so it's just probably blazingly fast. And even if it's not fast, like given that, like what I find interesting about this use case is that well, if you just have one graph, right, and it doesn't change a lot, then you just let's say do a forward prop, like once a day. Let's say you get some new features. That's fine. So to me, like this is, I mean, feel free to correct me or if I'm mistaken, but to me, this sounds like the contribution of the paper. It's like I have a large, like gigantic graph, right? And I want to partition this thing on multiple machines. And then what I do is I learn the clusters that are best representative via gradient descent. And then I can put these on a bunch of different devices. But to me, it still seems like I'm not clear. What is the loss function here? Like oh, would it be the difference based on the prediction you would get from the clustering but to that like because to me like it just seems like well like you're clustering it your loss should still be the same it's just that the cost to load data would increase but I don't see why your error function so they primarily do node classification tasks right yeah oh so then they only limit the analysis to a neighborhood I see okay okay got it so basically limit neighbors to device. Okay, this makes a lot of sense. So this is okay. Let's do the Bronstein blog post. Michael and I follow each other on Twitter. He always posts like cool stuff, like just like from proteins to, I know he works at physics. I don't know how involved he is in some of the more applied stuff there. If I'm not mistaken, he's also a professor, right? Imperial College. Oh, interesting. He gets to work from the UK at Twitter. That's kind of cool. Oh yeah, he is based in the UK. Oh, he looks like a young guy, by the way. I thought he was older. Geometric deep learning, these shapes. Oh, interesting. He was in graphics too. Spectral methods, diffusion geometry. I've been like looking for such like an excuse to start getting into differential geometry. I don't know, like I just feel though like basically post COVID, I feel like a lot of research labs started taking close to zero risk because they're just like, what's gonna numerical geometry on non-remaining shapes? This thing. Oh wow, this is like such an old book. Like this looks legit. Wait, let me differential remaining geometry. No, they're not here anymore. Okay, I'm gonna just write a note for myself. Like ask Michael for his lectures. A lot of the people in my group work in differential geometry. Oh, interesting. Like I'm guessing that like are you like working at a like are you working at a research lab or are you in a university? Because in university, I totally get it. Like people, I think have a much higher risk tolerance in academia than in industry in general. I feel like for the most part, like in industry, it's like I will it's not even like just ML. It's like some specific algorithm. It's like you know ResNet 50, yeah, BERT, base, and then maybe some MLP, just thrown in there. And I think these are sort of the algorithms I've seen people use. I think everything else sort of seems has been really exotic with the people I work with. And obviously, I don't want to generalize to all labs, but like I do meet a lot of people at different labs, and the ones actually with work in production, that's what they're doing. So you're talking about other researchers at university. You just graduated from undergrad. Oh, congrats! Like, yeah, I mean, like I think it's just like a cool space to be in. Maybe I think you'll be interested in some of this stuff. Like, there was this book that I really loved uh, that sort of got me interested in some of this stuff. Like, I wouldn't say I'm a geometer by any. So I'm at Facebook now, but there's some people working on differential geometry. Oh, I guess like in their VR teams or something, right? Like, here, check this out. So here, for example, like where was it? Rigid body motions in the plane. So, like for example, like this book, what it does is it gives like a sort of topological approach to doing robotics, uh, and so they really cover like different like the Euclidean group, different rotation group, like SO3, SE3, like all that cool stuff. And so this was sort of like my gateway into some of this stuff, but I never actually went deep into differential geometry. Oh, just unfair, yeah, like that's what I figured. Like, although you know what's sort of interesting, like Max Nickel and Brandon Amos, Max Nickel. Multi-relational data. Oh, interesting. Oh, interesting. So this is sort of tying back to the knowledge graph use cases because those are also just one giant graph. And I would imagine just Facebook to, you know, have one of the largest, if not the largest after Google's. Uh, this is very cool. And so the next person is Brandon Amos. Facial recognition. I'm gonna what's these guys. Input convex neural networks. Okay, so it seems like this is by far his most popular paper. So cameras are becoming ubiquitous in the Internet of Things. Okay, the facial recognition library. Let's see, Max. Three-way for collective learning on multi-relational data. Max Nickel and Brandon. Very cool. All right. So let's see, where were we? By Fabrizio Fasca, Emanuele Rossi. I think I've heard this name before. Twitter has a London office? I didn't know. Okay. And then Fabula AI. Oh, they got acquired. Oh, I see. Actually, like here, this is a pro tip, by the way, guys. So, if you ever go to a website and it's down, go to the Internet Archive and go Fabula. Let's see what they did. Okay. Can't hide anything. I'm just like sort of curious, like what their company was about. Like, I'm guessing it's something related with knowledge bases, I guess. Like, Twitter blog, Fabula. So they're not part of Twitter. Oh, I see. Oh, fake news detection. Oh, with graphs. Interesting. Interesting. Okay, okay. This is great stuff. Okay. Oh, by the way, Horace, if you do know of like a top differential geometry book that you'd recommend, please let me know. I think I've had trouble finding a good one. The one was like there was one guy that like I think it was at CMU that always had this cool book. Yeah, Keenan Crane is the guy I was thinking about. He always like such has such pretty stuff on his. This is so dope. Okay. Until recently, most of the research has been developing on new GNN models and testing them on small graphs, and relatively little effort has been invested in dealing with large-scale applications. On the other hand, industrial problems often deal with giant graphs, such as Twitter or Facebook social networks. So, in a nutshell, graph aggregating features feature the fusion across adjacent nodes. Uh, why is why is scaling graph neural networks challenging? In the aforementioned node-wise prediction problem, the nodes play the role of samples on which the GNN is trained, are drawn from some distribution, allows to decompose the loss function into individual sample contributions and employ SGD. So virtually every deep neural network architecture uh, today is trained via many batches. Oh, interesting. I like this characterization a lot, actually. So basically, basically, this makes many batching impossible. Like makes sorry. So a graph is one large uh, interrelated example. So, in many early works on graph neural networks, the problems were swept under the carpet. So, architectures such as GCN, MONET were trained using full batch gradient descent. This has led to the necessity of the whole adjacency matrix of the graph. Okay, yeah, so we talked about this before. So the first work to tackle this was graph safe. So in order to compute the training loss on a single node with an L layer graph, only the L neighbors of that node are necessary, as further nodes are not. Oh, L hop, I see. Okay. So there's like another form of pooling. So if we construct a batch with B training nodes, each with its own independent L hop neighborhood, we get to a memory complexity of VKL independent nodes of the graph. So a notable drawback of graph state is that sample nodes might appear multiple times, thus potentially introducing a lot of redundant computation. Uh, so multiple follow-up works focused on improving the sampling of mini batches in order to remove redundant and make maths more efficient. So there's clustering. Then at each batch, the model is trained on one cluster. This allows the nodes in each batch to be as tightly connected as possible. Oh, interesting. Okay. Yes, then this is, how do I rename this? Right? Unit. So GraphSame proposes instead a general probabilistic graph sampler by sampling subgraphs of the original graph. It's also important to note that one of the advantages of sampling is that during training, it acts as a sort of edgewise dropout, just regularizes the model. I feel like whenever you know people have some strategy in deep learning that just like loses information, they go like, oh, it regularizes the model, like dropout. Uh, yeah, I think it's almost somewhat always true. Uh, the extent to which it's possible to design simple sampling-free architectures for node-wise classification problems. There are a few reasons. So instances of node classification problems may significantly vary from one another. To the best of our knowledge, no work so far has systemically studied when sampling actually provides positive effects other than just alleviating computational complexity. Second, the implementation of sampling streams introduces additional complexity, and we believe strong sampling-free scalable baseline architecture is appealing. Whether depth is needed. Oh, that's what you were referring to, right? Like, do we need? Oh, is it? Do we need graph network? I just need to read everything by Michael. I think I thought I already followed him. He has a lot of posts. Like message passing graph neural networks suck. So I mean, like, how would you do it, right? Like in this case, like, would you just say like, we're gonna stop doing this, or do you have like, I mean, let's say you weren't bottlenecked by hardware or anything like that. Like, what would your ideal kind of algorithm look like? I will say, by the way, that almost everyone I talk to now are like, we're investigating transformers. Come on, man. Like, it's just like absolutely everything's gonna be decimated. Like that's why I think like I don't know if we're gonna have like I'm waiting for a paper saying like fully connected neural networks is all you need, and then just like put that on a giant GPU and just you're good to go. Uh, so by the way, like again, but with transformers you get the same problem with large graphs, right? Like you still can't fit it. You can't like unless you cluster it or something like that. For small graphs it may work, sure, but I think like for a small enough graph, it just seems like the problem isn't hard enough that almost like an arbitrary architecture. So if you're operating on a program's abstract syntax tree, oh, I see. I see. So it would be like but still relatively small graphs, right? Like what's the syntax tree gonna look like in a? Like you're gonna have thousands of nodes, but you're not gonna have millions, at least for any sort of reasonable program. Or you could always like break apart code. I think uh, you could just say like, okay, like anything that's in this namespace I want to look at. So there's sort of a natural way you can cluster stuff. Yeah, for sure. Link whatever you want. I know some people get anal about links, but like it's just like it looks like I see like, oh, I see. Uh yeah, like it's up to you there. Like cause like it the stream will be like the whole history of the stream will be recorded. So if you said I'm Horace and someone watched it, it may not be the best idea. Feel free to, like, don't DM it if you don't want to. I'll say that. Uh, but yeah, so simple fixed aggregators were shown to outperform many more complex ones. Okay, fixed neighborhood aggregators. Oh, I see. Uh, I will say though, I do have, I have like also like an ICLR paper I've been really psyched about. It just got submitted. So also like I guess when it's when the review when reviewer number two is like done bashing it, like I'll be sure to send it to you on Twitter or GitHub or something. Outperforms for a lot of node classification benchmarks. You can outperform GNNs. Oh, like with the sort of fixed idea that Michael's talking about here. With just MLP linear layers and a variant of label propagation. Oh, interesting. MLP linear layers. Oh, I see. But isn't it layer propagation like that kind of uh isn't layer propagation sort of similar to message passing conceptually? Isn't it just like a different, or is it just like totally different? Maybe like let me do this because oh, it's like this is completely unsupervised. I guess that's the difference, right? Like you initialize some labels. There's those in random order. The highest frequency among the neighbors. Oh, I see. Operates on label. Oh, oh well, it's not okay. Yeah, it's a good point. I mean, like, yeah, like I guess there's no loss, right? It's just almost like a deterministic algorithm that you would. Oh no, it's because you're putting it in a random order here. There's zero parameters. Yeah. That's what I meant. Uh, that's interesting because then, okay, so let's sort of think about the characteristics of this kind of stuff, right? Because if you have like, I'm assuming also what's interesting about your approach is that the models are probably tiny, right? Or it's like the opposite. Like, did it work with a tiny model that you want to run really fast, or was it like one gigantic model that runs really slow, but at least then you don't have to deal with these problems around like device loading or sharding or anything like that. I guess I'll say this: I'm really looking forward to reading your paper. Like, I think once it's ready, it's ready. But like, I'll be sure to set us some sort of notification on Google Scholar or something. OBGN product. I mean, it's still like pretty damn large, right? Like, it's larger than what they had uh in the clustering paper, like by far, right? And Oh, I see. So I should expect to see your name on this leaderboard soon then. That's gonna be good stuff. Oh yeah, I've seen Matthias Fay. Is he the PyTorch guy? Yeah, he is. So where we at? So that uses 137 less parameters and runs 100 times faster. That's very interesting. And are you running on CPU or GPU for now? Tesla V100. Okay, interesting. So this is using a GPU, right? Like, so you said like, I mean, it would use the sort of clustering approach you talked about. V100s have 32 gigs of memory. I see. That makes sense actually. So if you're dealing like if OBG if the paper's data set was around like 56 gigs, then yeah, this would fit on the whole thing, and then maybe even without clustering, it would run just fine. Yeah, this is kind of nuts actually. You can just like add cart, just like get it home. I'm tempted, you know. Like, what are these numbers like? Okay, so 8 of them with 512 gigs of RAM. I see. So this is the thing you want, right? Like ultimately, but you can just do with the one. So wait, what I'm curious about the leaderboards is that all of them seem to only be reporting accuracy, right? Like no one seems to be reporting like throughput or training speed in this case. I know this is just like not common in machine learning in general, but for me that's also what would be interesting here, just because these data sets are just like so massive in the first place. But it sounds like you're trying to change that, right? Like you said like you're making it 100 times faster. I think that's a big deal, which is kind of a proxy for runtime. Yeah, yeah, that's what I figured. Yeah, I guess number of params really, but like yeah, look at this. Like it's just like this is like okay, I'm using like a million, and then it's like 200,000. Like this is kind of cool, right? Like I think this work is more impressive than this work, for example. Turns out it's the same. It's the same lab. But what's the difference actually? Oh wow, like the it's really cutthroat here. Oh, and I see here the MLP stuff. Like there is a difference, but it's not as big as I would expect, right? Like this just seems to fit on a GTX. Wait, how? Like so they must be using clustering. Okay, wait, is there code here? Are you serious? Is it Matthias? Like 1, 2, 3, 4, 5, 6, 7, 8. Okay, sure, Matthias. It's a they considered using yeah, Matthias Fay is an author of the OGB. Yeah, I see. It's just funny how like he just shows up in all the like it's just so many times in the benchmark. I'm curious about this code, for example. Oh, I see. He just has them all here. I think I follow him on GitHub. Yeah, I do. Strain, touch the grad, data set. Okay. Where's the model? Wait, you're serious? That's it? Okay. Wow. I mean, but that's still impressive, right? Like it's just saying like yes, people beat him on the leaderboard with more complex stuff, but just being like, okay, here's one line of code, and the rest is just like, I mean, yeah, okay, this is the fourth proper like linear layer ReLU dropout. Like really, Softmax? Like, okay, sure. Oh, wait, well, so yeah, so these names are all starting to look good. Where does Weiha work? PhD student. So you don't need to batch on products if you're just using NMLP. Jur's student. Oh, I see. And so Jur, chief scientist at Pinterest. Oh, wow. Okay. Oh, I see. And then they get to do graphs for recommendations there. I see. So that's probably his segue into that. But it sounds like he does a lot more stuff in general, like stat formulas. It's just like all forms of graph. Like I think GNN sounds like a small subset of what he's interested in. Oh, I see. I should. Has he written any book tutorial? This has been really good stuff. So Horace, like honestly, thank you so much. Like I actually I feel like I learned so much from you during the last hour. So this is good stuff.